Welcome to The Explainer. Today, we're going to talk about a discovery that absolutely shattered classical physics and really gave birth to the entire quantum age. Okay, let's just dive right into this. I mean, think about it. It seems pretty obvious, right? A brighter light should have more power. But a simple experiment way back in the late 19th century revealed something, well, something deeply strange. Something that physicists at the time just could not explain.
So before we get into that big puzzle, let's kind of set the stage. Let's understand what the normal world of physics looked like back then.
See, for centuries, physicists were pretty darn certain about one thing. Light is a continuous wave of energy. They pictured it just like a wave in the ocean, just washing over things, transferring its energy smoothly and continuously. The brighter the light, the bigger the wave, and the more energy it carried. Simple, made perfect sense, or so they thought.
So this leads us to the photoelectric effect. The setup for this experiment was ridiculously simple. You shine a light on a piece of metal and just watch the electrons get knocked off. Scientists call these little guys photoelectrons. Now this wasn't the surprise. In fact, the wave theory actually predicted this would happen. The idea was that the light wave would just keep hitting an electron until it soaked up enough energy to finally break free.
Right, but here's the crucial point. This is where it all falls apart. The results of this super simple experiment made absolutely zero sense according to that nice, neat wave theory of light.
Yeah, what they expected to happen and what actually happened, well, they were two completely different stories. The nice, comfortable world of classical physics was about to get turned completely upside down.
Okay, now this is where it gets really interesting. Just look at how every single prediction completely failed. So for instance, they figured if you make the light brighter, increase the intensity, the electrons should fly off with more energy. Makes sense, right? But in reality, nope. More electrons flew off, but each one had the exact same energy. Even stranger, if you used a low-frequency light, like red light, nothing happened. No electrons came off at all. It didn't matter how bright you made it or how long you waited. The old theory was just completely wrong.
So you can see the problem, right? It was a total contradiction. What on earth was going on? Physics had hit a brick wall. The rules were broken, and that beautiful, elegant theory of light as a wave just could not explain these totally bizarre results. The field needed a brand new idea.
And that big idea? Well, it came in 1905. And it came from a young, unassuming patent clerk named Albert Einstein, who came up with something truly radical.
So what was this crazy idea? Einstein basically said, hey, what if light isn't a continuous wave at all? What if, instead, it travels in tiny individual packets of energy, kind of like a stream of microscopic bullets? He called them light quanta, but we know them today as photons.
And this was the absolute key to the whole puzzle. A photon's energy, he said, depends only on its frequency, that is, its color, and not on the light's intensity or its brightness. So think of it this way. Low-frequency red light is like a stream of ping-pong balls. High-frequency ultraviolet light, that's a stream of baseballs. Making the light brighter is just like throwing more balls. It doesn't change the power of any single one of them. And you can really see that difference in energy visualized right here. A high-frequency photon, our baseball, it's got a huge impact. But a low-frequency one, the ping-pong ball, has very little. Again, making the light brighter just means you're throwing more ping-pong balls. You're not magically turning them into baseballs.
Okay, so once you have this idea of a photon, this concept of light as a particle, well, the entire mystery of the photoelectric effect suddenly snaps into place. It all makes perfect sense.
It's all about a one-to-one collision. A single, high-energy photon, our baseball, slams into the metal. In that instant, it transfers all of its energy to a single electron. Now the electron has to use some of that energy just to escape its bond with the atom. That's called the work function. Think of it like an exit fee. Whatever energy is left over becomes the electron's speed, its kinetic energy. And that totally explains the threshold frequency. If the photon doesn't have enough energy to pay that escape cost, the electron goes nowhere. You need a baseball, not a ping-pong ball, to knock that electron out of the park.
This whole photon idea also explains why the electrons fly off pretty much instantly. There's no waiting around, no time lag for wave energy to slowly build up. The transfer happens in a flash, in less than a billionth of a second, in fact, the very moment that single photon hits.
And what's so incredible is that Einstein managed to capture this entire revolutionary theory in one simple, powerful equation. An equation that perfectly predicted all the experimental results and tied everything together just beautifully.
So here it is. The equation basically says the electron's final speed, its maximum kinetic energy, that's the Kmax, is simply equal to the energy of the incoming photon, which is that h nu part, minus the energy it needed to escape, that W, the work function. It was a perfect, elegant explanation that matched all the data. Absolutely brilliant.
So why does all this matter? What you should really take away from this is that Einstein's solution did way more than just solve one weird little puzzle in physics. It completely blew up our understanding of reality itself.
I mean, think about the legacy here. This single idea proved that light can act like a particle. It established this mind-bending concept of wave-particle duality. It became a foundational pillar for all of quantum mechanics, and it underpins so much of the technology we use every single day, from the sensor in your phone's camera to the solar panels powering our world. This showed us that light lives a double life. Sometimes it's a wave, sometimes it's a particle, and that opened the door to the strange and wonderful quantum world.
And that kind of leaves us with a really fascinating thought, doesn't it? If light lives this strange double life, what else in our universe does? This discovery didn't just solve a problem, it revealed a fundamental, weird duality in nature itself, making us question the very essence of everything around us.